The James Webb Space Telescope just discovered something that has scientists questioning everything they thought they knew about the universe. 300 galaxies shining brightly in the earliest moments of cosmic history, appearing in places where they simply should not exist. These ancient light sources are challenging the very foundation of how we understand the birth and growth of galaxies. The problem is not just that they are there, the problem is that they are way too bright, possibly way too massive, and definitely way too early. According to our current understanding of the universe, these galaxies had no business forming so quickly after the Big Bang. Yet there they are, glowing defiantly in the data, daring us to explain them. This is not a small puzzle, this is a cosmic crime scene, and the evidence is forcing astronomers to reconsider some of their most fundamental assumptions about how the universe works. To understand why these 300 galaxies are so shocking, we need to step back and look at the bigger picture. We need to understand the rules that govern the cosmos, the timeline that dictates when galaxies should form, and the delicate processes that allow stars and galaxies to come into being. Only then can we appreciate just how impossible these discoveries really are. Think of it this way: the universe has rules, just like any game. These rules dictate how matter behaves, how gravity works, and how structures like stars and galaxies can form. For decades, astronomers have been refining these rules, testing them against observations, and building a comprehensive model of how the universe evolved from the Big Bang to the present day. This model, called the Lambda Cold Dark Matter model, has been remarkably successful. It explains the cosmic microwave background, the distribution of galaxies across space, and the large-scale structure of the universe. It is the bedrock of modern cosmology, the foundation upon which our understanding of the cosmos is built. But now the James Webb Space Telescope has found something that does not fit the rules. 300 galaxies that are too bright, too massive, and too early to exist according to the Lambda Cold Dark Matter model. It is as if we have been playing a game of cosmic chess, confident in our understanding of how the pieces move, only to discover that some of the pieces are moving in ways that should not be possible. This discovery is forcing astronomers to ask fundamental questions. Are the rules wrong? Are we missing something important? Or is there a different explanation that we have not considered yet? Let's start with the universe itself. The cosmos is unimaginably vast, containing billions upon billions of galaxies, each filled with billions of stars. Our own Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. And it is just one galaxy among an estimated 2 trillion galaxies in the observable universe. The sheer scale is almost impossible to grasp. If you tried to count all the stars in the universe, counting one star per second, it would take you trillions of years to finish. But it was not always this way. The universe had a beginning, and that beginning was nothing like the organized, structured cosmos we see today. Roughly 13.8 billion years ago, everything that exists today was compressed into an infinitely small, infinitely dense point. This is not just all the matter in the universe crammed together. It is space itself, time itself, and all the energy that would ever exist, compressed into a single point smaller than an atom. Then, in an instant that defies our everyday understanding of physics, the Big Bang occurred. Space itself began expanding, and with it came the birth of matter, energy, time, and the very fabric of reality. This was not an explosion into space, but an expansion of space itself, carrying matter along with it. In those first moments, the universe was a seething ocean of particles, far too hot and chaotic for anything like stars or galaxies to form. The temperature was so high that not even atoms could exist. Matter existed as a soup of fundamental particles, quarks, and electrons, bouncing around at incredible speeds. Imagine the inside of a star, but millions of times hotter, filling all of space. This was the state of the universe in its first moments. As the universe expanded, it cooled. Within the first few minutes, the simplest atomic nuclei began to form, mostly hydrogen and helium, with tiny traces of lithium. This process, called Big Bang nucleosynthesis, created the raw materials that would eventually form stars and galaxies. But it would take hundreds of thousands of years before the universe cooled enough for atoms to form completely. During this time, the universe was opaque, filled with a fog of free electrons that scattered light in all directions. No light could travel far without being absorbed and re-emitted. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei, forming the first complete atoms. This moment is known as recombination, and it marked a fundamental change in the universe. Suddenly, light could travel freely through space. The fog cleared, and the universe became transparent. This first light, released at the moment of recombination, is still traveling through the universe today. We call it the cosmic microwave background, a faint glow of ancient light that fills the entire sky. This light has been stretched by the expansion of the universe, shifting from visible light into the microwave part of the spectrum. But it carries with it a snapshot of what the universe looked like when it was just 380,000 years old. Astronomers have studied the cosmic microwave background in incredible detail, and it has revealed tiny fluctuations in temperature, tiny differences in density from one region of space to another. These fluctuations, no more than 1 part in 100,000, were the seeds from which all the structure in the universe would grow. After recombination, the cosmos entered a period known as the Dark Ages, a time when there were no stars, no galaxies, nothing but vast clouds of neutral hydrogen gas drifting through the expanding void. The universe was truly dark during this period. The cosmic microwave background light was fading as the universe expanded, and no new sources of light had yet turned on. The Dark Ages lasted for tens of millions of years, perhaps even 100 million years or more. During this time, the tiny density fluctuations left over from the Big Bang were growing. Regions that were slightly denser than their surroundings had slightly stronger gravity, which pulled in more matter, making them even denser. This process, called gravitational collapse, was slow at first but accelerated over time. Eventually, gravity began to work its magic. The densest regions of the universe began to collapse into the first structures. But these were not yet galaxies in the way we think of them today. They were small, dark clumps of matter, mostly hydrogen gas, held together by gravity. These clumps, or halos, ranged in size from a few thousand times the mass of the Sun to millions of times the mass of the Sun. Within these halos, the gas continued to collapse, becoming denser and denser, pulling in more gas from the surrounding space. As the gas collapsed, it heated up. This might seem counterintuitive. Why would something get hotter as it collapses? The answer lies in gravity. When gas falls inward under gravity, it speeds up, and that motion is converted into heat. The faster the gas falls, the hotter it gets. Eventually, in the very densest regions at the centers of these collapsing halos, the gas became so hot and so dense that a new process began. Hydrogen atoms started to collide with so much energy that they fused together, creating helium and releasing enormous amounts of energy in the process. This is nuclear fusion, the same process that powers the Sun today. When nuclear fusion ignited in these dense cores, the first stars were born. This moment, when the first stars turned on and began to shine, marked the end of the Dark Ages and the beginning of an era called the Cosmic Dawn. The universe was no longer completely dark. It was beginning to light up with the glow of the first stars. These first stars were unlike anything we see today. They were massive, hot, and short-lived, burning through their fuel in just a few million years before exploding as supernovae. The reason they were so different from modern stars has to do with the composition of the gas from which they formed. Modern stars form from gas that contains a small amount of heavy elements like carbon, nitrogen, oxygen, and iron, which were created by earlier generations of stars. These heavy elements act like a coolant, helping the gas to cool down and fragment into smaller pieces. This is why modern stars come in a wide range of sizes, from small red dwarfs that are a tenth the mass of the Sun to massive blue giants that are dozens of times the mass of the Sun. But the first stars formed from gas that was almost entirely hydrogen and helium, with virtually no heavy elements. Without heavy elements to help the gas cool, the gas could not fragment into small pieces. Instead, it collapsed into very large, very massive stars, perhaps 50 to 100 times the mass of the Sun, or even larger. These stars were incredibly hot and bright, shining with the light of millions of suns. They burned through their hydrogen fuel at a furious rate, living fast and dying young. When they exhausted their fuel, they exploded as supernovae, blasting their outer layers into space and leaving behind either a neutron star or a black hole. But even though they were short-lived, these first stars were crucial to the evolution of the universe. They produced the first heavy elements, seeding the surrounding gas with carbon, oxygen, and other elements that would be incorporated into the next generation of stars. They also began the process of ionizing the hydrogen gas around them. The intense ultraviolet light from these massive stars could strip electrons off hydrogen atoms, turning neutral hydrogen into ionized hydrogen. This process, called reionization, slowly cleared the fog of neutral hydrogen that filled the universe, making space transparent to ultraviolet light for the first time since the Dark Ages began. Over time, these early stars began to cluster together, forming the first small galaxies. This is where the hierarchical nature of galaxy formation, predicted by the Lambda Cold Dark Matter model, comes into play. According to the model, galaxies grow slowly and hierarchically. Small clumps of matter merge to form bigger clumps, which merge to form even bigger ones, and so on. This process is gradual and takes a lot of time. Think of it like building a snowman. You start with a small snowball and gradually add more and more snow, rolling the snowball around until it becomes large enough to form the body of the snowman. You do not start with a giant snowball, you build it up slowly over time. In the same way, galaxies are supposed to build up slowly over time. In the first few 100 million years after the Big Bang, the universe should only have had small, faint proto-galaxies, nothing like the massive, bright structures we see today. These proto-galaxies would have contained perhaps a few million stars, maybe tens of millions at most, not the billions of stars found in a galaxy like the Milky Way. They would have been faint, small, and scattered across the universe, slowly merging with each other to form larger structures. Over billions of years, these small proto-galaxies would merge again and again, gradually building up into the massive galaxies we see in the universe today. The Lambda Cold Dark Matter model has been incredibly successful at explaining many features of the universe. It correctly predicts the patterns we see in the cosmic microwave background, the way galaxies are distributed across space, and the ages of the oldest stars. It explains why galaxies are often found in clusters, and why the universe has a web-like structure with galaxies strung along filaments of dark matter like beads on a string. The model has been tested against countless observations, and time and again it has passed those tests. It is the foundation upon which modern cosmology is built, and it has given us a coherent, comprehensive picture of how the universe evolved from the Big Bang to the present day. But here's where things get interesting and where the story takes an unexpected turn. When the James Webb Space Telescope turned its powerful gaze toward the distant universe, it did not see what the Lambda Cold Dark Matter model predicted. Instead, it found hundreds of bright, possibly massive galaxies shining in an era when they should barely exist. These galaxies are so distant that their light has been traveling toward us for over 13 billion years, crossing the vast expanse of space to reach our telescopes. We are seeing them as they were just 300 to 700 million years after the Big Bang, during the cosmic dawn, when the universe was less than 5% of its current age. And they are not faint, struggling proto-galaxies with a few million stars scattered across a small region of space. They are luminous, vibrant, and in some cases, potentially as massive as the Milky Way, which contains hundreds of billions of stars. This should not be possible. According to the Lambda Cold Dark Matter model, galaxies of this size and brightness should not exist for at least another few 100 million years, perhaps even 1 billion years or more. To put this in perspective, imagine you are watching a time-lapse video of a forest growing. You expect to see seeds sprouting into saplings, then slowly growing into mature trees over many years, perhaps decades or even centuries. Time serves. The process is gradual, predictable, and slow. But instead, you see full-grown oak trees towering hundreds of feet into the air, appearing just minutes after the seeds are planted. Not only do the trees appear, but they are already fully formed, with thick trunks, spreading branches, and lush canopies of leaves. That is essentially what astronomers are observing with these 300 galaxies. The timeline does not make sense. The universe simply did not have enough time to build such large, bright galaxies so quickly after the Big Bang. It is as if someone hit the fast-forward button on cosmic evolution, skipping over hundreds of millions of years of slow, gradual growth. The discovery of these 300 galaxies is forcing scientists to ask some very uncomfortable questions. Are our models of galaxy formation wrong? Have we been misunderstanding the processes that govern how galaxies grow? Is there something fundamental we do not understand about the early universe? Or is there a simpler explanation that we have overlooked, something that could resolve the mystery without requiring major changes to our theories? These are not easy questions to answer, and astronomers are still working to figure out what these galaxies are telling us. But one thing is clear: the universe is not behaving the way we expected it to behave, and that is both exciting and deeply puzzling. Before we dive into the possible answers, we need to understand how astronomers even know these galaxies are so far away in the first place. Measuring distances in the universe is not like measuring distances on Earth. You cannot simply stretch a tape measure across the cosmos, and you cannot send a spaceship to these galaxies to measure how far they are. They are much too distant for that. The light from these galaxies has been traveling toward us for over 13 billion years. And in all that time, the galaxies themselves have moved even farther away due to the expansion of the universe. So how do astronomers figure out how far away a galaxy is, and more importantly, how do they know when that galaxy existed in cosmic history? The answer lies in a property of light called redshift. Light behaves like a wave, and like all waves, it has a wavelength which determines its color. Blue light has a short wavelength, while red light has a longer wavelength. If you have ever seen a rainbow, you have seen the full spectrum of visible light with blue and violet on one end and red on the other. Now here is the key. When an object is moving away from us, the light it emits gets stretched out, shifting toward the red end of the spectrum. This is called redshift, and the faster an object is moving away, the greater its redshift. You might have experienced a similar effect with sound. When a car drives past you, the pitch of the engine sound seems to drop as the car moves away. This is called the Doppler effect, and it happens because the sound waves get stretched out. Redshift is the same idea, but with light instead of sound. Because the universe is expanding, distant galaxies are moving away from us, and their light is redshifted. The farther away a galaxy is, the more time its light has spent traveling through the expanding universe, and the more redshifted it becomes. By measuring how much a galaxy's light has been redshifted, astronomers can calculate how far away it is, and crucially, how far back in time we are seeing it. A galaxy with a low redshift, say a redshift of 0.1, is relatively close and recent, perhaps 1 billion or 2 billion light years away. A galaxy with a high redshift, say a redshift of 10 or higher, is incredibly distant and ancient, existing when the universe was less than 1 billion years old. The 300 galaxies discovered by the James Webb Space Telescope have very high redshifts, meaning they are among the most distant objects ever observed. We are seeing them as they appeared when the universe was less than 1 billion years old, during a time when the first galaxies were just beginning to form. Some of these galaxies have redshifts around 8 or 9, others have redshifts around 10 or 11, and a few might have redshifts even higher than that. Each of these redshift values corresponds to a specific time in the universe's history, allowing astronomers to place these galaxies in the cosmic timeline and understand when they existed. But there is a catch, and it is an important one that goes to the heart of the controversy surrounding these galaxies. The initial redshift measurements for these galaxies are based on a technique called photometry, which involves looking at the brightness of a galaxy in different filters of light. Imagine taking a photograph of the night sky using a camera that can only see red light, then taking another photograph using a camera that can only see blue light, and another using a camera that can only see green light. By comparing how bright a galaxy appears in each of these photographs, astronomers can estimate its redshift. This works because galaxies have characteristic patterns in their light, and these patterns shift to redder wavelengths as the redshift increases. For example, hydrogen atoms emit light at very specific wavelengths, creating bright lines in the spectrum of a galaxy. One of these lines, called the Lyman alpha line, occurs in the ultraviolet part of the spectrum for nearby galaxies. But for a very distant galaxy with a high redshift, the Lyman alpha line gets shifted all the way into the visible or even infrared part of the spectrum. By looking for these shifted spectral features in the photometric data, astronomers can estimate the redshift of a galaxy. However, photometric redshift measurements are not perfect. They can be fooled by certain types of galaxies, such as those that are very dusty or contain older stars, which naturally emit more red light. Think about it this way. If you see a car that looks red, you might assume it is painted red. But what if the car is actually blue, but you are looking at it through red-tinted glasses? You would think the car is red even though it is actually blue. The same problem can happen with galaxies. If a galaxy is covered in dust, the dust absorbs blue light and lets red light through, making the galaxy appear redder than it actually is. This can make a relatively nearby, dusty galaxy look like it is an extremely distant galaxy with a very high redshift. Similarly, if a galaxy contains mostly old stars, which naturally emit more red light, it can also appear redder than a galaxy with young, hot stars. To be absolutely sure of a galaxy's distance, astronomers need to use a more precise technique called spectroscopy. This involves splitting the light from a galaxy into its component colors, like a rainbow, and looking for specific patterns in the spectrum that reveal the galaxy's true redshift. Spectroscopy is much more detailed than photometry. Instead of just measuring the brightness of a galaxy in a few broad filters, spectroscopy measures the brightness at thousands of different wavelengths, creating a highly detailed picture of the galaxy's light. This allows astronomers to identify specific spectral lines, such as the hydrogen lines we mentioned earlier, and measure exactly how much they have been shifted. Spectroscopy is considered the gold standard for measuring distances, and it is the technique that astronomers trust the most. If spectroscopy shows that a galaxy has a redshift of 10, you can be very confident that the galaxy is indeed at that distance. But spectroscopy is also much more time-consuming and difficult than photometry. To perform spectroscopy on a faint, distant galaxy, a telescope needs to collect light from that galaxy for many hours, sometimes even days. This is because distant galaxies are incredibly faint, and it takes a long time to gather enough light to create a detailed spectrum. In contrast, photometry can be done much more quickly, often in just a few minutes per galaxy. The James Webb Space Telescope has only had time to perform detailed spectroscopy on a small fraction of the hundreds of candidate galaxies it has discovered. For most of them, astronomers are still relying on photometric estimates. This has led to some controversy, and it is one of the reasons why astronomers are being cautious about interpreting the results. A few of the earliest extreme galaxy candidates discovered by James Webb, which initially appeared to be impossibly massive, were later found to be closer and less extraordinary when spectroscopy was performed. For example, one galaxy that was initially thought to have a redshift of around 12, placing it just 200 million years after the Big Bang, was later found to have a redshift of only around 4, placing it about 1.5 billion years after the Big Bang. This is still an interesting galaxy, but it is not nearly as extreme as initially thought. But importantly, and this is crucial, some of the extreme candidates have been confirmed by spectroscopy, proving that at least some of these impossibly bright early galaxies are real. A group of 6 galaxies, initially discovered by James Webb in 2022, were thought to be so massive that they challenged the Lambda Cold Dark Matter model. Spectroscopic follow-up observations confirmed that these galaxies are indeed at very high redshifts, ranging from about 7 to 9, placing them in the first 500 million years after the Big Bang. While some of their estimated masses were revised downward after spectroscopy, they are still far more massive and brighter than expected for galaxies at that time. This proves that the phenomenon of impossibly bright early galaxies is real, not just an artifact of measurement errors. So what makes these 300 galaxies so special, and why are astronomers so excited and puzzled by them? The key issue is their brightness and potentially their mass. When astronomers look at the light coming from these galaxies, they see objects that are shining with the brightness of billions of suns. To put that in perspective, our own sun produces an enormous amount of light, enough to light up the entire solar system and make life possible on Earth. Now imagine a billion suns all shining together. That is how bright some of these early galaxies appear to be. In some cases, the galaxies are even brighter, perhaps 10 billion or even 100 billion times the brightness of the sun. Now, brightness alone is not necessarily a problem. A galaxy could be bright simply because it is forming a lot of stars or because it contains a very bright, supermassive black hole at its center. The real problem comes when astronomers try to figure out how massive these galaxies are, meaning how many stars they contain. To estimate a galaxy's mass, astronomers look at its brightness and make assumptions about what is producing that light. If the light is coming from stars, then the brightness tells you roughly how many stars there are. Young, hot stars are very bright, while old, cool stars are much dimmer. By looking at the color of the galaxy's light, astronomers can estimate the types of stars it contains, and from that calculate how many stars there are in total. In some cases, the estimated stellar mass, the total mass of all the stars in the galaxy, is staggering. Some of these galaxies could contain 1.3 billion solar masses of stars, meaning they have more than 1 billion times the mass of our Sun locked up in stars. To put that in perspective, that is roughly equivalent to 10% of the mass of the Milky Way in stars. And remember, the Milky Way is a mature, fully formed galaxy that has been growing for over 13 billion years. These early galaxies are achieving a similar mass in just a few 100 million years. Others could be even more massive, with estimates reaching over 30 billion solar masses, or even higher in some extreme cases. That would make them more massive than the Milky Way, even though they are forming when the universe is less than 5% of its current age. These numbers are mind-boggling, especially considering how young the universe was when these galaxies formed. To understand why this is such a problem, let us think about how much time it takes to build a galaxy. Stars do not form instantly. The process of turning gas into stars takes time, and it is not perfectly efficient. You start with a cloud of gas, mostly hydrogen with a bit of helium. Gravity pulls the gas together, causing it to collapse. As the gas collapses, it heats up and eventually becomes dense enough to ignite nuclear fusion, forming a star. But not all the gas in the cloud becomes part of the star. Some of it is blown away by the star's radiation, some of it is left behind as diffuse gas, and some of it might form a disk around the star that later becomes planets. In modern galaxies like the Milky Way, only a small fraction of the available gas actually gets converted into stars over the galaxy's lifetime. Maybe 10%, maybe 20% depending on the galaxy. Much of the gas is blown away by stellar winds, supernova explosions, and other energetic processes before it can form stars. This inefficiency is a key part of why galaxies grow slowly over time. They cannot turn all their gas into stars instantly. They have to do it gradually over billions of years, with much of the gas being recycled or lost along the way. This is why the Milky Way, after over 13 billion years of evolution, still has plenty of gas left and is still forming new stars today, albeit at a modest rate of about 1 to 2 solar masses per year. In the early universe, conditions were different, and this might have allowed for more efficient star formation. The gas was pristine, containing almost entirely hydrogen and helium with very few heavy elements. This might have made the gas easier to collapse and potentially more efficient at forming stars, because there were fewer processes to disrupt the collapse. But even with these favorable conditions, there are fundamental limits to how fast stars can form. The process of collapse takes time. Gas has to fall inward under gravity, and it cannot fall faster than the speed of free fall, which is determined by the strength of gravity and the density of the gas. Even under ideal conditions, it takes millions of years for a cloud of gas to collapse and form stars. To form a galaxy with billions of solar masses of stars in just a few 100 million years would require an extraordinarily high star formation rate, far exceeding anything we see in the universe today. Let us put some numbers on this. Modern galaxies like the Milky Way form stars at a rate of about 1 to 2 solar masses per year, meaning they turn enough gas into new stars to equal the mass of 1 or 2 suns every year. That might sound like a lot, but it is actually quite modest compared to what would be needed to form these early galaxies. If you formed stars at a rate of 1 solar mass per year for 100 million years, you would only end up with 100 million solar masses of stars. To get to 1 billion solar masses, you would need to form stars at a rate of 10 solar masses per year for 100 million years, or 100 solar masses per year for 10 million years. But even that is not enough to explain the most extreme galaxies, which might have tens of billions of solar masses. To build a galaxy with 30 billion solar masses in, say, 300 million years, you would need to form stars at a rate of 100 solar masses per year, sustained continuously for that entire period. That is 50 to 100 times higher than the star formation rate in the Milky Way today. Some of the most active star-forming galaxies in the universe today, known as starburst galaxies, can form stars at rates of hundreds or even thousands of solar masses per year. These galaxies are going through temporary bursts of intense star formation, often triggered by collisions or mergers with other galaxies. During a collision, gas from both galaxies is compressed, triggering a huge wave of star formation that can last for tens or hundreds of millions of years. But even these extreme examples are not enough to explain the early galaxies seen by James Webb, for a couple of reasons. First, starburst galaxies today are usually the result of mergers between two or more large galaxies. And in the early universe, galaxies were much smaller, so mergers would not produce the same kind of extreme starbursts. Second, starburst episodes are temporary. They last for a few tens of millions of years, maybe 100 million years at most, and then the star formation rate drops back down as the gas is used up or blown away. To build a galaxy with tens of billions of solar masses, you would need to sustain a high star formation rate for hundreds of millions of years, not just a few tens of millions of years. To build a galaxy with billions of solar masses of stars in just a few hundred million years, the star formation rate would need to be almost constant and incredibly high, perhaps approaching 100% efficiency. This would mean that nearly all the gas in the galaxy is being turned into stars with very little waste. Such extreme efficiency has never been observed in the modern universe, and there is no clear mechanism that would allow it to happen in the early universe either. Every process we know of that forms stars is inherently inefficient. Stars emit radiation that pushes against the surrounding gas. They create stellar winds that blow gas out of the galaxy. And when massive stars explode as supernovae, they inject enormous amounts of energy into the surrounding gas, heating it up and preventing it from collapsing to form new stars. Yet, if the mass estimates for these galaxies are correct, that is what must have occurred. The galaxies must have been forming stars at rates of tens or hundreds of solar masses per year, sustained for hundreds of millions of years, with very little gas being lost or wasted. This is the heart of the mystery. The galaxies are too bright and too massive for the time they had to grow. They are like impossible cities, fully built and bustling with life, appearing in a wilderness where there should only be small villages. And just like impossible cities, their existence demands an explanation, something that can account for how they grew so fast and so large in such a short amount of time. To understand why this is such a problem, we need to think about how galaxies form and how stars are made. Stars are born when clouds of gas collapse under gravity, becoming dense and hot enough to ignite nuclear fusion in their cores. The process of turning gas into stars is called star formation, and it is not perfectly efficient. In modern galaxies, only a small fraction of the available gas actually gets converted into stars. Much of the gas is blown away by stellar winds, supernova explosions, and other energetic processes before it can form stars. This inefficiency is a key part of why galaxies grow slowly over time. In the early universe, conditions were different. The gas was pristine, containing almost entirely hydrogen and helium with very few heavy elements. This made the gas easier to collapse and potentially more efficient at forming stars. But even with these favorable conditions, there are limits to how fast stars can form. The process takes time, and the universe was simply not old enough for these galaxies to have accumulated so many stars so quickly, at least according to the standard models. To form a galaxy with billions of solar masses of stars in just a few hundred million years would require an extraordinarily high star formation rate, far exceeding anything we see in the universe today. Let's put some numbers on this. Modern galaxies like the Milky Way form stars at a rate of about 1 to 2 solar masses per year, meaning they turn enough gas into new stars to equal the mass of 1 or 2 suns. Every year, that might sound like a lot, but it is actually quite modest. Some of the most active star-forming galaxies in the universe today, known as starburst galaxies, can form stars at rates of hundreds or even thousands of solar masses per year. These galaxies are going through temporary bursts of intense star formation, often triggered by collisions or mergers with other galaxies. Even these extreme examples are not enough to explain the early galaxies seen by James Webb. To build a galaxy with billions of solar masses of stars in just a few hundred million years, the star formation rate would need to be almost constant and incredibly high, perhaps approaching 100% efficiency. This would mean that nearly all the gas in the galaxy is being turned into stars with very little waste. Such extreme efficiency has never been observed in the modern universe, and there is no clear mechanism that would allow it to happen in the early universe either. Yet, if the mass estimates for these galaxies are correct, that is what must have occurred. This is the heart of the mystery. The galaxies are too bright and too massive for the time they had to grow. Now, let's talk about how the James Webb Space Telescope actually found these galaxies, because the story of their discovery is almost as impressive as the galaxies themselves. James Webb is not just a bigger version of earlier telescopes. It is a fundamentally different kind of instrument designed specifically to study the early universe in ways that were impossible before. The telescope is uniquely suited to this task because it observes in the infrared part of the electromagnetic spectrum. To understand why this matters, we need to think about how light works and how it changes as it travels across the universe. Light comes in many forms, from radio waves with wavelengths of meters or even kilometers, to visible light with wavelengths of a few hundred nanometers, to X-rays with wavelengths smaller than an atom. Infrared light sits between visible light and radio waves, with wavelengths ranging from about 700 nanometers to a few hundred micrometers. Our eyes cannot see infrared light, but we can feel it as heat. Infrared cameras can detect this light and create images from it. Infrared light has longer wavelengths than visible light, which gives it two important properties that make it ideal for studying the early universe. First, infrared light can penetrate through dust. Dust is a problem for astronomers because it blocks visible light. When you try to look at a distant galaxy, the dust in that galaxy and the dust in our own galaxy can absorb the visible light, making the galaxy appear dimmer or even invisible. But infrared light has longer wavelengths, which allow it to pass through dust without being absorbed. This means that infrared telescopes can see objects that are hidden from visible light telescopes. Second, and more importantly for the study of the early universe, infrared light is the red-shifted light from the most distant galaxies. When we look at a galaxy from the cosmic dawn, a galaxy that formed just a few 100 million years after the Big Bang, its light has been traveling through space for over 13 billion years. During that time, the universe has been expanding, and as it expands, it stretches the light that is traveling through it. This stretching shifts the light to longer wavelengths, moving it from the ultraviolet and visible part of the spectrum into the infrared. For the most distant galaxies, galaxies with redshifts of 10 or higher, almost all of their light has been shifted into the infrared. This is why earlier telescopes, like the Hubble Space Telescope, had a harder time seeing these distant objects. Hubble primarily observed invisible and near-infrared light, which limited its ability to see the most red-shifted galaxies. Hubble could see galaxies with redshifts up to about 10 or 11, but it struggled to see anything beyond that. The galaxies were simply too red, too shifted into the infrared, for Hubble's cameras to detect them clearly. James Webb, on the other hand, is equipped with powerful infrared instruments, including the near-infrared camera and the mid-infrared instrument. The near-infrared camera, or NIR-CAM, is the primary imaging instrument on James Webb. It can take pictures of the universe in infrared light, capturing wavelengths from about 600 nanometers to 5 micrometers. This allows it to see galaxies with redshifts up to about 20 or even higher, covering the entire cosmic dawn and reaching back to the very first galaxies that ever formed. The mid-infrared instrument, or MIRI, observes at even longer wavelengths, from about 5 micrometers to 28 micrometers. MIRI is used to study the cooler objects in the universe, such as dust clouds, forming planets, and distant galaxies shrouded in dust. These instruments allow James Webb to peer deeper into the universe than ever before, capturing light from galaxies that formed just a few 100 million years after the Big Bang. But having powerful infrared cameras is only part of the story. The telescope also uses a clever technique called the dropout technique to identify these distant galaxies. Here is how it works, and it is a beautiful piece of detective work that shows just how ingenious astronomers have become at finding distant objects. Light from a very distant galaxy is redshifted, meaning it appears redder than it would if the galaxy were closer. But there is another effect at play, and it is this effect that makes the dropout technique possible. As light travels through space, it can be absorbed by neutral hydrogen gas. In the early universe, before the first stars ionized the surrounding gas, space was filled with neutral hydrogen. This hydrogen absorbs light at a specific wavelength known as the Lyman alpha wavelength, which is about 121 nanometers in the ultraviolet part of the spectrum. If a photon of light has exactly this wavelength or a shorter wavelength, it will be absorbed by neutral hydrogen. This creates a sharp cutoff in the spectrum of a distant galaxy, known as the Lyman break. For a galaxy at low redshift close to us, the Lyman break occurs in the ultraviolet, which we cannot observe from Earth because our atmosphere blocks ultraviolet light. But for a distant galaxy with a high redshift, the Lyman break gets redshifted along with the rest of the galaxy's light. For a galaxy with a redshift of around 6, the Lyman break shifts into the visible part of the spectrum around 700 to 800 nanometers. For a galaxy with a redshift of 10, the Lyman break shifts into the near-infrared around 1.3 micrometers. This means that when astronomers look at a distant galaxy through different filters, it will appear bright in redder filters, where the galaxy's light is not absorbed but will suddenly drop out or disappear in bluer filters, where the Lyman break cuts off the light. Imagine you're looking at a galaxy through a red filter and it appears bright and clear. Then you switch to a blue filter and suddenly the galaxy disappears. This dropout is the signature of a very distant galaxy, and it is the primary method used to identify candidates for follow-up observations. By looking for galaxies that drop out in progressively redder filters, astronomers can estimate how far away they are. A galaxy that drops out in a blue filter but appears in green and red filters probably has a redshift around 3 or 4. A galaxy that drops out in green filters but appears in red and infrared filters probably has a redshift around 6 to 8. And a galaxy that appears only in the deepest infrared filters probably has a redshift of 10 or higher. The 300 galaxies discovered by James Webb were identified using this dropout technique, combined with measurements of their brightness in multiple infrared filters. Astronomers took deep images of the sky using several different filters, each sensitive to a different range of wavelengths. Then they looked for objects that appeared bright in some filters but dropped out in others, indicating a high redshift. But as we mentioned earlier, the dropout technique is not foolproof. Some galaxies can mimic the signature of a very distant galaxy if they are dusty or contain older stars. Dust absorbs blue light and re-emits it as infrared light, making a dusty galaxy appear redder than it actually is. Similarly, older stars naturally emit more red light than young, hot stars. This means that a relatively nearby, dusty galaxy could be mistaken for an extremely distant one if astronomers rely only on photometry. This is why spectroscopy is so important. By measuring the exact wavelengths of light coming from a galaxy, astronomers can identify specific spectral lines, patterns in the light that correspond to known elements. These spectral lines are redshifted by the same amount as the rest of the galaxy's light, providing a precise measurement of its distance. So far, only a small number of the candidate galaxies have been confirmed with spectroscopy, but the results have been promising. Some of the extreme early galaxies have been confirmed to be exactly as distant as the photometric measurements suggested. This proves that at least some of the impossible galaxies are real. However, spectroscopy has also revealed that some candidates are not as distant as initially thought. In a few cases, what appeared to be an extremely distant massive galaxy turned out to be a closer galaxy with unusual properties. This has led to a healthy debate in the astronomical community about just how many of these 300 candidates will hold up under closer scrutiny. Regardless of how many are ultimately confirmed, the existence of even a handful of extremely bright early galaxies is enough to challenge the standard model of galaxy formation. The question is, what is causing these galaxies to be so bright and apparently so massive? There are several leading theories, and each one has its own implications for our understanding of the universe. Let's explore them one by one, starting with the most straightforward explanation. Though even the straightforward explanation requires some remarkable assumptions. Perhaps the early universe was simply better at forming stars than we thought. In this scenario, the galaxies are not breaking the rules of physics. They are not violating any fundamental laws. Instead, the conditions in the early universe allowed for extremely efficient star formation, turning nearly all the available gas into stars in a very short period of time. This idea is sometimes called the superheated star factory hypothesis, and it is based on the idea that the early universe was a very different place from the universe we see today. In the early universe, gas clouds were pristine, containing almost no heavy elements. Modern gas clouds, the ones that form stars and galaxies like the Milky Way today, contain about 2% heavy elements by mass. That might not sound like much, but those heavy elements play a crucial role in the star formation process. Elements like carbon, nitrogen, and oxygen can radiate away energy very efficiently, helping the gas to cool down. When gas cools, it contracts under gravity, becoming denser and eventually collapsing to form stars. The heavy elements act like a coolant, speeding up the cooling process and making star formation more efficient. But in the early universe, the gas had virtually no heavy elements. It was almost entirely hydrogen and helium with just tiny traces of lithium. Without heavy elements to help the gas cool, you might think that star formation would be slower, not faster. But the situation is more complex than that. Without heavy elements, the gas cannot fragment into small pieces as easily. In modern star-forming regions, gas clouds break up into many small clumps, each of which forms a star. This is why we see a wide range of star sizes, from tiny red dwarfs to massive blue giants. But in the early universe, without heavy elements to help the gas cool and fragment, the gas might have collapsed into fewer, larger clumps, forming very massive stars. These massive first-generation stars, sometimes called population 3 stars, would have been incredibly hot and bright, perhaps 50 to 100 times the mass of the Sun, or even larger. They would have burned through their fuel very quickly, living for just a few million years before exploding as supernovae. But while they lived, they would have shone with incredible brightness, perhaps 1,000,000 times brighter than the Sun. If a galaxy was forming mostly these massive, bright stars, it would appear very luminous, even if it did not have that many stars in total. This could explain why the early galaxies appear so bright. They are not necessarily more massive than expected. They are just forming very bright stars, which makes them shine more intensely. Additionally, the density of matter was much higher in the early universe, which would have increased the rate of gravitational collapse. In the modern universe, matter is spread out over vast distances. Galaxies are separated by millions of light years, and even within galaxies, the gas is relatively diffuse. But in the early universe, everything was closer together. The universe was smaller, and matter was more concentrated. This higher density would have made gravity stronger, pulling gas together more quickly and accelerating the process of star formation. If these factors combined in just the right way, it is conceivable that early galaxies could have achieved star formation rates far exceeding anything we see today. Some models suggest that star formation efficiencies in the early universe could have approached 100%, meaning almost all the gas in a galaxy was turned into stars within a few 100 million years. To understand what this means, consider that in modern galaxies, the star formation efficiency is very low. In the Milky Way, only about 10 to 20% of the gas has been converted into stars over the entire 13 billion year history of the galaxy. The rest of the gas is either still floating around in the galaxy, waiting to form stars in the future, or it has been expelled from the galaxy entirely by stellar winds and supernova explosions. But if the early universe had star formation efficiencies approaching 100%, that would mean that nearly all the gas in a galaxy was turned into stars, leaving almost nothing behind. If this is true, then the brightness of these early galaxies is simply a reflection of their incredibly high star formation rates. They are not necessarily more massive than expected in terms of the total amount of matter they contain. They are just forming stars so rapidly and forming such bright stars that they shine with the brightness of billions of suns. Over time, as the gas is used up and the star formation slows down, these galaxies would settle into more normal structures, like the galaxies we see in the universe today. The massive, bright stars would explode as supernovae, leaving behind neutron stars and black holes. The heavy elements created in these explosions would enrich the gas, making it easier to cool and fragment, leading to the formation of smaller, less massive stars in subsequent generations. This explanation has the advantage of not requiring any major changes to the laws of physics or the Lambda Cold Dark Matter model. It simply suggests that the early universe was a more dynamic and active place than we previously realized, with physical conditions that allowed for much more efficient star formation than we see today. It fits within the existing framework of cosmology, requiring only that we adjust our expectations about how quickly and efficiently stars could form in the first few 100 million years after the Big Bang. However, there are significant problems with this idea, problems that make many astronomers skeptical that it can fully explain the bright early galaxies. For one thing, achieving nearly 100% star formation efficiency is extremely difficult, perhaps even impossible. Even in the most favorable conditions, there are processes that prevent gas from collapsing into stars. When stars form, they do not do so quietly. They emit powerful radiation, intense ultraviolet light, that heats the surrounding gas and pushes against it. This radiation pressure can actually stop gas from falling into the star, creating a natural limit on how massive a star can become. The most massive stars we know of today are around 200 to 300 times the mass of the Sun, and they are constantly fighting against their own radiation, which is trying to blow them apart. Stellar winds from massive stars also blow gas out of galaxies. These winds are streams of particles flowing away from the star at speeds of thousands of kilometers per second. They carry away mass and energy, pushing gas out into the space between galaxies where it cannot form stars. For a galaxy to achieve 100% star formation efficiency, it would have to overcome these winds and hold onto its gas, which is very difficult. Then there are supernova explosions. When a massive star exhausts its fuel and collapses, it explodes in a supernova, one of the most violent events in the universe. A single supernova releases as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. This energy blasts into the surrounding gas, heating it to millions of degrees and driving powerful shockwaves that can clear out entire regions of a galaxy. These feedback mechanisms are an important part of galaxy evolution, and they should have been active in the early universe as well, perhaps even more so because the massive stars in the early universe would have produced even more energetic supernovae. It is hard to see how early galaxies could have overcome these obstacles to achieve such extreme star formation rates and efficiencies. You cannot just turn off the laws of physics. Stars will always emit radiation, stellar winds will always blow gas away, and supernovae will always inject energy into the surrounding gas. These processes are fundamental to how stars work, and they place limits on how efficiently gas can be converted into stars. Time JWST. Moreover, if star formation efficiencies were so high in the early universe, we would expect to see other evidence of this in the data, evidence that has not yet been clearly observed. For example, we might expect to see a larger population of very small, dense galaxies that exhausted their gas supply quickly and stopped forming stars. So far, the observations do not clearly support this prediction. The star formation efficiency puzzle extends even deeper when we consider the physics of how individual stars form. When a cloud of gas collapses to form a star, only a tiny fraction of the original cloud's mass ends up in the star itself. The rest is either blown away or remains as diffuse gas. This is because the process of star formation is inherently messy and wasteful. Young stars emit powerful winds and radiation that push against the surrounding gas, counteracting gravity and slowing down the collapse. In the modern universe, this means that star formation is inefficient by default. For the early galaxies to form stars at the rates required to explain their brightness, something fundamental must have been different. Perhaps the first generation of stars, known as population 3 stars, formed in a way that was more efficient than later generations. These stars would have been made of pure hydrogen and helium, with no heavy elements to complicate the chemistry. The absence of heavy elements means the gas could not cool as efficiently, which paradoxically might have led to the formation of very massive stars that burned brightly but briefly. But even if population 3 stars were more efficient at forming, they still would have created feedback that limited further star formation. The intense radiation and supernova explosions from these massive stars would have heated the surrounding gas and blown it out of the galaxy, stopping star formation in its tracks. To keep forming stars at the incredible rates required to build these massive early galaxies, there must have been a way to replenish the gas supply continuously. This could have happened through the accretion of fresh gas from the surrounding intergalactic medium, but even this process has limits. Gas falling into a galaxy heats up as it is compressed, and if it gets too hot, it cannot collapse to form stars. One possibility is that the early galaxies were fed by cold gas streams, narrow channels of cool gas that could flow directly into the galaxy without being heated too much. These cold streams are predicted by simulations of galaxy formation in the early universe, and they could have provided a steady supply of fresh fuel for star formation. If cold streams were common in the early universe, they might explain how these galaxies were able to sustain such high star formation rates for long enough to build up billions of solar masses of stars. However, even with cold streams, the star formation rates required are still pushing the limits of what is physically plausible. Another factor to consider is the role of dark matter in early galaxy formation. Dark matter makes up the majority of the mass in the universe, and it plays a crucial role in the formation of galaxies. Dark matter does not interact with light or normal matter except through gravity, so it can collapse into dense structures without being hindered by radiation pressure or other feedback mechanisms. These dark matter structures, known as dark matter halos, act as gravitational wells that attract normal matter and provide the framework for galaxy formation. In the early universe, the smallest dark matter halos would have been the first to collapse, and they would have been the sites of the first star formation. But there is a limit to how massive a dark matter halo can grow in a given amount of time. The growth of dark matter halos is governed by the expansion of the universe and the rate at which smaller halos can merge to form larger ones. In the first few 100 million years after the Big Bang, even the most massive dark matter halos would have been relatively small by modern standards. To form a galaxy with tens of billions of solar masses of stars, you would need a dark matter halo that is much more massive than what the standard models predict should exist at that time. This is another piece of the puzzle that does not quite fit. Some researchers have suggested that the early universe might have had a population of unusually massive dark matter halos, sometimes called overmassive halos, that formed through rare early mergers of smaller halos. If such overmassive halos existed, they could have provided the gravitational potential needed to hold on to large amounts of gas and form massive galaxies more quickly. However, these overmassive halos should be extremely rare, and finding 300 of them in a relatively small patch of sky would be surprising. This brings us to another question. Are all 300 of these candidate galaxies truly as massive as they appear, or are some of them being boosted in brightness by other mechanisms? This leads us to the second major explanation for the brightness of these early galaxies. Perhaps the light we are seeing is not coming from stars at all, but from something even more exotic, supermassive black holes. At the center of most large galaxies, including our own Milky Way, there is a supermassive black hole, an object with millions or even billions of times the mass of the Sun, compressed into a region smaller than our solar system. These black holes are not directly visible because they do not emit light. However, when matter falls into a black hole, it forms a swirling disk of gas called an accretion disk. As the gas spirals inward, it heats up to millions of degrees and emits enormous amounts of light across the entire electromagnetic spectrum. This glowing accretion disk can outshine all the stars in the galaxy combined, making the galaxy appear incredibly bright. Galaxies with actively feeding supermassive black holes are called active galactic nuclei. If some of the 300 galaxies discovered by James Webb are actually active galactic nuclei rather than star-forming galaxies, this could explain their extreme brightness without requiring impossibly high star formation rates. There is some evidence to support this idea. In recent years, astronomers have discovered a population of compact, extremely bright objects in the early universe, often referred to as little red dots. These objects are small, intensely red, and very luminous, which is consistent with what we would expect from an active galactic nucleus. Spectroscopic observations of some of these objects have confirmed the presence of supermassive black holes, providing strong evidence that at least some of the bright early galaxies are powered by black holes rather than stars. If this is the case, then the apparent mass of these galaxies could be much lower than initially estimated. The brightness is not coming from billions of stars, but from a single, extremely massive black hole at the galaxy's center. However, this explanation also raises its own set of questions. If these galaxies contain supermassive black holes, how did those black holes get so big so quickly? Supermassive black holes are thought to grow by accreting matter over time, but the process is slow. A black hole can only grow as fast as it can pull in surrounding gas, and there are limits to how quickly this can happen, set by the physics of the accretion disk. When matter falls into a black hole, it releases energy in the form of radiation. This radiation pushes against the infalling matter, creating an outward pressure that opposes gravity. At a certain point, the outward radiation pressure becomes so strong that it prevents any more matter from falling in. This limit is known as the Eddington limit, and it sets a maximum rate at which a black hole can grow. For a black hole to grow from a stellar mass seed, formed from the collapse of a massive star, to a supermassive black hole with millions or billions of solar masses, would typically take billions of years, even if it were accreting at the Eddington limit the entire time. Yet the galaxies discovered by James Webb are being observed when the universe was only a few 100 million years old. This does not leave enough time for supermassive black holes to grow through normal accretion, at least not starting from stellar mass seeds. One possibility is that the early universe had a population of intermediate mass black holes, which served as seeds for the supermassive black holes we see today. These seed black holes could have formed from the collapse of the very first stars, known as population 3 stars, which were much more massive than typical stars today. If population 3 stars were massive enough, they could have collapsed directly into black holes with hundreds or even thousands of solar masses. Alternatively, intermediate mass black holes could have formed through the direct collapse of massive gas clouds without ever forming a star first. Under certain conditions, a cloud of gas can collapse so rapidly that it bypasses the normal star formation process and forms a black hole directly. These direct collapse black holes could have masses of tens of thousands or even hundreds of thousands of solar masses right from the start. If such seed black holes existed in the early universe, they could have grown into supermassive black holes much more quickly than black holes formed from stellar collapse. But even with seed black holes, the growth rates required to explain the brightest early galaxies are still extraordinarily high. To grow a seed black hole with 10,000 solar masses into a supermassive black hole with 1 billion solar masses in just a few 100 million years would require the black hole to accrete matter at or above the Eddington limit for the entire duration. This is possible, but it would require a continuous supply of gas and very specific conditions to prevent feedback from the black hole from shutting down the accretion. Some researchers have proposed that early black holes could have grown through super Eddington accretion, where the black hole accretes matter at rates higher than the Eddington limit. This could happen if the infalling gas is very dense and optically thick, trapping the radiation inside the accretion disk and preventing it from pushing against the infalling matter. Super Eddington accretion is a controversial idea because it requires very specific conditions, and it is not clear how common it would have been in the early universe. However, if it did occur, it could explain how supermassive black holes grew so quickly. Another possibility is that the black holes grew through mergers with other black holes. In the early universe, galaxies were smaller and closer together, which would have made mergers more common. If a galaxy containing a massive black hole merged with another galaxy, the two black holes could eventually merge as well, creating an even more massive black hole. Through repeated mergers, black holes could have grown very quickly, possibly fast enough to explain the supermassive black holes seen in the early universe. But there is a limit to how much black hole growth can be attributed to mergers. Each merger requires the two black holes to spiral together and coalesce, a process that takes time. Additionally, mergers would have been more common in dense regions of the universe, where galaxies were clustered together. If the 300 bright early galaxies are all powered by supermassive black holes that grew through mergers, we would expect them to be found in regions of high galaxy density. Observations so far do not clearly show this pattern, although more data is needed to be sure. The black hole hypothesis is intriguing and it is supported by some evidence, but it is not a complete solution to the mystery of the bright early galaxies. There is another intriguing possibility. What if the Lambda Cold Dark Matter model itself is not quite right? This is the most radical of the explanations, but it is one that some astronomers are beginning to take seriously. The Lambda Cold Dark Matter model has been incredibly successful, but it is not without its puzzles. There are a few small discrepancies between the model's predictions and certain observations, and the discovery of these impossibly bright early galaxies could be another hint that something is missing. One idea is that the early universe contained a form of energy known as early dark energy. Dark energy is the mysterious force that is causing the expansion of the universe to accelerate today. but early dark energy is a hypothetical form of energy that would have been present in the early universe and then decayed away. If early dark energy existed, it could have affected the rate at which matter collapsed to form the first structures. Specifically, it could have accelerated the formation of galaxies in the first few 100 million years after the Big Bang, allowing large structures to form more quickly than the standard Lambda Cold Dark Matter model predicts. This would not require any changes to the laws of physics, but it would mean that our cosmological model is incomplete. Early dark energy is an attractive idea because it could solve several problems in cosmology at once. In addition to explaining the bright early galaxies, it could also help resolve other tensions in the Lambda Cold Dark Matter model, such as the discrepancy in measurements of the Hubble constant, which describes the rate of expansion of the universe. However, early dark energy is still a speculative idea, and there is not yet strong independent evidence for its existence. If early dark energy did exist, we would expect to see other signatures of it in the data, such as changes in the cosmic microwave background, or the distribution of galaxies at different times in the universe's history. Astronomers are actively searching for these signatures, but so far the evidence is inconclusive. Another possibility is that the process of structure formation itself was faster than we thought. Some theoretical models, sometimes referred to as fast-track models, suggest that under certain conditions, the collapse of matter in the early universe could have been much more rapid, leading to the formation of large galaxies earlier than expected. These models often involve modifications to the standard Lambda Cold Dark Matter framework, such as changes to the properties of dark matter or the addition of new physical processes that enhance the growth of structure. For example, some models propose that dark matter could have interacted with itself in the early universe in ways that are not accounted for in the standard model. These self-interactions could have altered the distribution of dark matter and sped up the collapse of the first structures. Other models suggest that there could have been primordial magnetic fields or other exotic phenomena in the early universe that affected how matter clumped together. These ideas are still in the early stages of development, and they need to be tested against a wide range of observations before they can be accepted. One of the challenges with modifying the Lambda Cold Dark Matter model is that the model is very successful at explaining a wide range of observations, from the cosmic microwave background to the large-scale structure of the universe. Any modification to the model needs to be able to reproduce all of these successes, while also explaining the new observations such as the bright early galaxies. This is a high bar to clear, and it is why most astronomers are cautious about proposing major changes to the Lambda Cold Dark Matter model. However, if the observations of the bright early galaxies continue to hold up under scrutiny, and if no other explanation can be found, then modifications to the model may become necessary. There is one more possibility that we need to consider, and it is perhaps the simplest of all. What if some of these galaxies are not as far away as we think? As we have discussed, the initial distance estimates for these galaxies are based on photometry, which can be fooled by certain types of galaxies. If a significant fraction of the 300 candidates turn out to be closer, less exotic galaxies, then the problem of impossibly bright early galaxies may not be as severe as it currently appears. This would not mean that the discoveries are unimportant. Even a smaller number of confirmed extreme early galaxies would still challenge our models. But it would take some of the pressure off the Lambda Cold Dark Matter model, the key to resolving this. Critical question is spectroscopy. Spectroscopy is the only way to definitively confirm the distances to these galaxies and determine whether they truly are the extreme objects they appear to be. When astronomers obtain a spectrum of a galaxy, they can identify specific emission and absorption lines that correspond to known elements. Hydrogen, helium, oxygen, carbon, and nitrogen all produce characteristic patterns in the spectrum. By measuring the wavelengths of these lines and comparing them to their rest wavelengths, the wavelengths they would have in a stationary galaxy, astronomers can calculate the exact redshift. This spectroscopic redshift is much more reliable than a photometric estimate. It is like the difference between estimating someone's age by looking at their photo versus asking them directly for their birth certificate. One method gives you a rough guess, while the other gives you a precise answer. Spectroscopy can also reveal whether a galaxy is actively forming stars, or whether its light is dominated by an active galactic nucleus, powered by a supermassive black hole. Star-forming galaxies show emission lines from hot gas clouds where new stars are being born. The strength and shape of these lines tell us how vigorously the galaxy is forming stars. Active galactic nuclei, on the other hand, show very broad emission lines produced by gas moving at thousands of kilometers per second near the black hole, along with strong emission from highly ionized atoms that require extremely energetic radiation to create. By looking at the spectrum, astronomers can distinguish between these two cases and understand what is really powering the galaxy's brightness. So far, James Webb has only had time to perform detailed spectroscopy on a small fraction of the hundreds of candidate galaxies it has discovered. This is not due to lack of interest or effort. Spectroscopy is simply much more time-consuming than photometry. A single spectroscopic observation of a faint, distant galaxy can take hours or even days of telescope time, depending on how faint the object is and how detailed a spectrum is needed. James Webb is an incredibly powerful telescope, but it can only look at one small patch of sky at a time. With thousands of interesting targets competing for observing time, and with each observation requiring careful planning and execution, it will take years to obtain spectroscopy for all 300 candidate galaxies. In the meantime, astronomers are prioritizing the most interesting candidates, those that appear to be the most massive or the most distant or the most puzzling, for follow-up observations. Time Schachters. As more spectroscopic data comes in, the picture is becoming clearer, though it is also becoming more nuanced and complex. Some of the candidate galaxies have been confirmed to be exactly as distant and as bright as the photometric measurements suggested. These confirmed cases prove that the phenomenon of impossibly bright early galaxies is real, not just a measurement error or an artifact of the observing technique. They demonstrate that the early universe was capable of producing structures that challenge our theoretical models. Others have turned out to be closer and less extreme than initially thought. In a few high-profile cases, what appeared to be an extremely distant, massive galaxy with a redshift of 12 or 13 turned out to be a closer galaxy with a redshift of 4 or 5. These galaxies are still interesting in their own right, but they do not pose the same challenge to the Lambda Cold Dark Matter model. The ratio of confirmed to rejected candidates will ultimately tell us a lot about the nature of the early universe. If most of the candidates are confirmed, it will be strong evidence that the early universe was indeed a more active and dynamic place than we thought, and it will put significant pressure on the Lambda Cold Dark Matter model to explain how so many massive galaxies could form so quickly. If only a small fraction are confirmed, perhaps 10 or 20%, it will suggest that the photometric measurements were systematically overestimating the distances to some galaxies, perhaps because of dust or unusual stellar populations. Even in this case, the confirmed galaxies would still be remarkable and would still require explanation, but the problem would be less severe than it initially appeared. The ongoing spectroscopic campaign is therefore crucial to understanding what we are really seeing. It is the difference between a revolution in cosmology and an interesting but ultimately manageable puzzle. Every new spectrum adds a piece to the puzzle, helping us to separate the truly extreme objects from the imposters. Beyond spectroscopy, there are other observations that can help us understand these mysterious galaxies. One powerful technique is to look for gravitational lensing, where the gravity of a massive foreground object, such as a galaxy cluster, bends and magnifies the light from a more distant background galaxy. When a distant galaxy happens to lie behind a massive galaxy cluster, its light is bent around the cluster, creating multiple distorted images of the galaxy. This gravitational lensing can magnify the galaxy's light by factors of 10, 100, or even 1,000, making it much easier to study. Several of the confirmed extreme early galaxies have been found in gravitationally lensed systems, allowing astronomers to study them in far greater detail than would otherwise be possible. Gravitational lensing not only magnifies the galaxy, but also allows astronomers to resolve its internal structure. Instead of seeing the galaxy as a single point of light, they can see individual star-forming regions, dust clouds, and other features within the galaxy. This provides crucial information about how the galaxy is forming stars and how its mass is distributed. In some cases, gravitational lensing has revealed that what appeared to be a single massive galaxy is actually several smaller galaxies in close proximity, merging together to form a larger structure. This is consistent with the hierarchical model of galaxy formation, where large galaxies form from the merger of smaller ones, and it suggests that at least some of the apparent mass in these early galaxies is real and not an artifact of measurement. Another important line of evidence comes from studying the cosmic microwave background in greater detail. The cosmic microwave background is the afterglow of the Big Bang, and it contains a wealth of information about the early universe encoded in tiny temperature fluctuations across the sky. These fluctuations tell us about the density of matter in the early universe, the properties of dark matter and dark energy, and the initial conditions that led to the formation of the first structures. By measuring the cosmic microwave background with ever greater precision, astronomers can test whether the Lambda Cold Dark Matter model correctly predicts the conditions that existed when the first galaxies were forming. If the Lambda Cold Dark Matter model is correct, the cosmic microwave background should show specific patterns that are consistent with the slow, hierarchical growth of structure. If modifications to the model are needed, such as the addition of early dark energy or changes to the properties of dark matter, these modifications would leave distinct signatures in the cosmic microwave background. Several experiments are currently underway or planned to measure the cosmic microwave background with unprecedented precision, including ground-based telescopes in Antarctica and Chile, balloon-borne experiments, and future space missions. These measurements will provide an independent test of the cosmological model and will help determine whether the bright early galaxies require new physics or can be explained within the existing framework. There is also the question of what happens to these early galaxies over time. Do they continue to grow and evolve into the massive elliptical galaxies we see in the universe today? Or do they burn out quickly, exhausting their gas supply and fading into obscurity? By studying galaxies at a range of different times in the universe's history, astronomers can trace the evolutionary path from the first galaxies to the mature galaxies we see today. This requires observations at many different redshifts, building up a complete picture of how galaxies change over cosmic time. James Webb is uniquely suited to this task because it can observe galaxies across a wide range of redshifts, from the earliest times at redshifts of 10 or higher, all the way down to relatively recent times at redshifts of 1 or 2. By comparing galaxies at different epochs, astronomers can see how star formation rates change over time, how galaxies merge and interact, and how supermassive black holes grow and influence their host galaxies. This evolutionary picture is essential for understanding whether the bright early galaxies are anomalies, rare flukes that do not fit into the normal pattern of galaxy evolution, or whether they are the ancestors of the galaxies we see today. If they are ancestors, then understanding how they formed and evolved is crucial to understanding the full history of the universe. If they are anomalies, then we need to figure out what made them different, and why they do not have many counterparts in the later universe. The discovery of these 300 galaxies also highlights the importance of large surveys that observe many objects across wide areas of sky. James Webb has conducted several deep field observations, staring at small patches of sky for long periods of time to detect the faintest possible objects. These deep fields have revealed the 300 candidate galaxies and have shown that bright, early galaxies are more common than expected. But to truly understand how common they are, and to place them in the broader context of galaxy formation, astronomers need to survey larger areas of sky. This will allow them to find not just a few hundred candidates, but thousands or even tens of thousands, providing a statistically robust sample that can be used to test theoretical models. Future space missions and ground-based observatories are being designed with this goal in mind. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will have a field of view 100 times larger than James Webb, allowing it to survey huge areas of sky and find rare objects like these bright early galaxies in large numbers. Ground-based telescopes equipped with adaptive optics, which corrects for the blurring effects of Earth's atmosphere, are also becoming more powerful and capable of studying distant galaxies. Together, these facilities will build a comprehensive census of galaxies in the early universe, providing the data needed to resolve the mystery of the bright early galaxies once and for all. There is also an important philosophical dimension to this discovery. The universe is not obligated to conform to our expectations. It does not care about our theories or our models. It simply is what it is, and our job as scientists is to observe it as carefully and objectively as possible, to build models that explain what we see, and to revise those models when new observations demand it. The bright early galaxies are a humbling reminder that the universe is more complex and more surprising than we often give it credit for. They challenge us to think more deeply, to question our assumptions, and to remain open to the possibility that we might be wrong about some fundamental aspects of cosmology. At the same time, this discovery is also a testament to the power of the scientific method. When faced with observations that do not fit the existing model, scientists do not simply dismiss them or sweep them under the rug. They take them seriously, investigate them rigorously, and consider all possible explanations, from the mundane to the revolutionary. They perform follow-up observations to confirm or refute the initial findings. They build new models and test them against the data. They debate and discuss, critique, and refine, always striving to get closer to the truth. This process is messy and sometimes slow, but it is also remarkably effective at uncovering the secrets of the universe. The 300 bright early galaxies are now the subject of intense study by astronomers around the world. Research papers are being published at a rapid pace, each one adding new insights and raising new questions. Conferences and workshops are being held to bring together experts to discuss the latest findings and to plan future observations. Graduate students are writing their dissertations on these galaxies, and they will carry the knowledge and the questions forward into the next generation of researchers. This is how science advances, not through sudden eureka moments, but through the steady accumulation of evidence and the gradual refinement of our understanding. So where does this leave us as we stand at this pivotal moment in astronomy? We are in a state of productive uncertainty. We have discovered something remarkable, something that challenges our understanding, but we do not yet have a definitive explanation. This is not a failure. It is exactly where we should be at this stage of the investigation. We have identified a problem, we have gathered the initial data, and we are now in the process of testing different hypotheses and collecting more evidence. The final answer may take years or even decades to emerge, but every step along the way brings us closer to understanding the true nature of these galaxies and the early universe in which they formed. The excitement in the astronomical community is palpable. Rarely do we encounter observations that so directly challenge fundamental aspects of our cosmological model. The bright early galaxies represent a genuine anomaly, something that demands explanation and that cannot be easily dismissed or ignored. Whether the explanation turns out to involve super-efficient star formation, rapidly growing supermassive black holes, modifications to our cosmological model, or some combination of these factors, the process of figuring it out will advance our understanding of the universe in profound ways. We will learn new things about star formation, about black hole growth, about dark matter and dark energy, and about the very earliest moments of cosmic history. There is something deeply satisfying about being confronted with a mystery that we do not immediately understand. It reminds us that despite all our technological sophistication and all our accumulated knowledge, the universe still has the power to surprise us. It keeps us humble and curious, always questioning, always seeking, never satisfied with easy answers. The 300 bright early galaxies are a gift in this sense. They are a reminder that the universe is not a closed book, that there are still profound questions to answer and discoveries to make. They inject new energy and excitement into the field of cosmology, attracting new students and researchers who want to be part of solving this puzzle. In a broader sense, the discovery of these galaxies also speaks to our place in the universe and our relationship with the cosmos. We are small, fragile beings living on a tiny planet orbiting an ordinary star in an unremarkable corner of a vast galaxy. Our entire existence spans just a few dozen years, a blink of an eye compared to the 13.8 billion year history of the universe. Yet despite our smallness and our brevity, we have managed to peer across billions of light years and billions of years of time, to witness the birth of galaxies and to question the fundamental nature of reality. This is an extraordinary achievement, one that should fill us with wonder and pride. The fact that we can even conceive of these questions, let alone begin to answer them, is a testament to the power of human intelligence and creativity. We have built instruments that can capture the faintest whispers of light from the edge of the observable universe. We have developed mathematical frameworks that can describe the behavior of the cosmos with stunning accuracy. We have created international collaborations that bring together thousands of scientists from dozens of countries, all working toward a common goal of understanding our cosmic origins. This is what humanity is capable of when we put our minds to it, when we prioritize knowledge and understanding over short-term gain. The 300 bright early galaxies are not just interesting from a scientific perspective, they are also deeply meaningful on a human level. They connect us to the vastness of space and time, reminding us that we are part of something much larger than ourselves. They inspire a sense of awe and wonder that transcends the technical details and the scientific jargon. When we look at an image of one of these ancient galaxies, we are seeing light that has been traveling for over 13 billion years. Light that left that galaxy when the universe was young and wild and still finding its form. That light has crossed unimaginable distances to reach us, carrying with it information about a time and place that no human will ever visit. This sense of connection to the cosmos is important. It gives us perspective on our own lives and our own problems. It reminds us that the universe is ancient and vast, and that our moment in cosmic history is fleeting but precious. It encourages us to think beyond our immediate concerns and to consider the long-term future of humanity and our place in the universe. If we can understand how the first galaxies formed, perhaps we can better understand our own origins and our own destiny. Perhaps we can learn something about how life and intelligence arise in the universe, and whether we are alone or part of a larger cosmic community. The journey of discovery that began with the first observations of these 300 galaxies is far from over. It will continue for many years, perhaps many decades, as astronomers collect more data, refine their models, and test new hypotheses. There will be setbacks and surprises, moments of confusion and moments of clarity. But through it all, we will be driven by the same curiosity and wonder that has always motivated human exploration, the desire to know, to understand, to see beyond the horizon. And in the end, whatever we discover about these galaxies will enrich our understanding of the universe and deepen our appreciation for the beauty and complexity of the cosmos. There is one more possibility that we need to consider, and it is perhaps the simplest of all. What if some of these galaxies are not as far away as we think? As we have discussed, the initial distance estimates for these galaxies are based on photometry, which can be fooled by certain types of galaxies. If a significant fraction of the 300 candidates turn out to be closer, less exotic galaxies, then the problem of impossibly bright early galaxies may not be as severe as it currently appears. This would not mean that the discoveries are unimportant. Even a smaller number of confirmed extreme early galaxies would still challenge our models, but it would take some of the pressure off the Lambda Cold Dark Matter model and suggest that the early universe was not quite as strange as the initial observations suggested. The only way to know for sure is to perform spectroscopy on as many of these candidates as possible. This is a slow and painstaking process, but it is essential for understanding what we are really looking at. James Webb is capable of performing high-quality spectroscopy, but it can only observe a limited number of objects at a time. Each spectroscopic observation can take hours or even days, depending on how faint the object is. Given that there are 300 candidate galaxies, it will take years to obtain spectroscopy for all of them. In the meantime, astronomers are prioritizing the most interesting candidates, those that appear to be the most massive or the most distant for follow-up observations. As more spectroscopic data comes in, the picture is becoming clearer. Some of the candidate galaxies have been confirmed to be exactly as distant and as bright as the photometric measurements suggested. Others have turned out to be closer and less extreme. The ratio of confirmed to rejected candidates will tell us a lot about the nature of the early universe. If most of the candidates are confirmed, it will be strong evidence that the early universe was indeed a more active and dynamic place than we thought, and it will put significant pressure on the Lambda Cold Dark Matter model. If only a small fraction are confirmed, it will suggest that the photometric measurements were systematically overestimating the distances to some galaxies, and it will be less of a challenge to the standard model. So where does this leave us? The discovery of 300 bright, possibly massive galaxies in the early universe is one of the most exciting and perplexing findings in modern astronomy. These galaxies are challenging our understanding of how the universe evolved in its first billion years, and they are forcing astronomers to consider a range of possible explanations, from extremely efficient star formation to rapidly growing supermassive black holes to potential modifications of the Lambda Cold Dark Matter model itself. Each of these explanations has its own strengths and weaknesses, and the truth may involve a combination of factors. What is clear is that the James Webb Space Telescope is giving us an unprecedented view of the early universe, and it is revealing a cosmos that is more complex and dynamic than we ever imagined. The 300 galaxies are not just data points. They are clues in a cosmic detective story, one that is still unfolding. As more spectroscopic observations are made, and as our models become more sophisticated, we will get a clearer picture of what these galaxies really are and what they tell us about the birth of the universe. For now, we are left with a tantalizing mystery, a population of ancient light sources that should not exist according to the rules we thought we knew. The stakes are high. If even a fraction of these galaxies are confirmed to be as extreme as they appear, it could mark the beginning of a revolution in cosmology. It could mean that the early universe was a far more active and energetic place than we realized, with galaxies forming stars at breakneck speeds or supermassive black holes growing to enormous sizes in record time. It could mean that our models of galaxy formation are missing key ingredients, or that the Lambda Cold Dark Matter model needs to be updated to include new physics. These are not small questions. They go to the heart of how we understand the universe and our place in it. But there is also a sense of excitement and wonder in all of this. The universe has surprised us before, and it will surprise us again. Every time we build a more powerful telescope or develop a new technique for observing the cosmos, we discover things that challenge our expectations. This is the nature of science. It is not about confirming what we already know. It is about exploring the unknown and being willing to revise our understanding when the evidence demands it. The 300 galaxies discovered by James Webb are a reminder that the universe is full of mysteries, and that we are only just beginning to unravel them. As we move forward, the job of astronomers will be to carefully test each of the possible explanations for these galaxies. This will involve more observations with James Webb and other telescopes, more detailed modeling of galaxy formation and black hole growth, and perhaps even new theoretical ideas that we have not yet considered. It will take time, but the payoff will be a deeper and richer understanding of the cosmos. We will learn how the first galaxies formed, how supermassive black holes came to be, and whether our fundamental models of cosmology need to be revised. These are some of the biggest questions in all of science, and the 300 galaxies are helping to guide us toward the answers. In the meantime, we can marvel at the sheer audacity of these ancient galaxies. They are shining beacons from a time when the universe was young and wild, a time when the rules of galaxy formation were still being written. They are a testament to the power of gravity, the resilience of matter, and the incredible complexity of the cosmos. They remind us that the universe is not a static, unchanging place, but a dynamic, evolving system, full of surprises and wonders. And they remind us that despite all our knowledge and technology, we are still learning, still exploring, still reaching out to understand the vast and beautiful universe that we call home. The discovery of these 300 galaxies is just the beginning. As James Webb continues to observe the distant universe, it will undoubtedly find more of these enigmatic objects. Each new discovery will add another piece to the puzzle, bringing us closer to a complete picture of the early universe. And as our understanding grows, we will be able to answer the questions that have been haunting astronomers since these galaxies were first detected. Are they powered by stars or black holes? Did the Lambda Cold Dark Matter model get something wrong? Or is there an entirely new phenomenon at play that we have not yet imagined? Whatever the answers turn out to be, one thing is certain. The universe is far stranger and more wonderful than we ever dared to imagine. It is a place where the impossible becomes possible, where the rules we thought were set in stone can be bent or broken, and where every new observation opens up new questions and new mysteries. The 300 galaxies are a perfect example of this. They are impossible, and yet they exist. They defy our expectations, and yet they are real. They challenge our models, and yet they offer us the opportunity to learn something profound about the nature of the cosmos. This is the essence of scientific discovery. It is the thrill of finding something you did not expect, the challenge of explaining something that seems impossible, and the satisfaction of slowly piecing together a deeper understanding of how the universe works. The 300 galaxies are a gift to astronomers, a chance to test their theories, refine their models, and push the boundaries of human knowledge. They are also a reminder that the universe does not owe us easy answers. It is complex, it is mysterious, and it is full of surprises. And that is exactly what makes it so fascinating. As we stand on the brink of a new era in astronomy, with James Webb and other next-generation telescopes revealing the secrets of the early universe, we can look forward to many more discoveries like this. We can expect to find more galaxies that challenge our expectations, more objects that push the limits of what we thought was possible, and more opportunities to learn about the cosmos. The journey is just beginning, and the 300 galaxies are our first glimpse of what lies ahead. They are a tantalizing hint of the wonders that await us as we peer deeper into the universe and further back in time. So what should we take away from all of this? First, we should recognize that the universe is a place of incredible diversity and complexity. The galaxies we see in the early universe are not all the same. Some may be powered by intense star formation, others by supermassive black holes, and still others by processes we do not yet understand. This diversity is a clue that the early universe was a dynamic and rapidly evolving place, where conditions varied widely from one region to another. Second, we should appreciate the power of modern astronomy and the incredible tools we have at our disposal. The James Webb Space Telescope is a marvel of engineering, capable of peering deeper into the universe than any telescope before it. Without James Webb, we would never have known about these 300 galaxies, and we would still be operating under the assumption that the early universe was a quiet, slowly evolving place. Third, we should embrace the uncertainty and the mystery. Science is not about having all the answers. It is about asking the right questions and being willing to follow the evidence wherever it leads. The 300 galaxies are a mystery, and we do not yet know what the solution is, but that is okay. Mysteries are what drive science forward. They inspire us to think creatively, to challenge our assumptions, and to push the boundaries of what is possible. The fact that we do not yet understand these galaxies is not a failure. It is an opportunity. It is a chance to learn something new, to refine our theories, and to deepen our understanding of the universe. Finally, we should remember that the universe is not finished revealing its secrets. The 300 galaxies are just the latest in a long line of discoveries that have challenged and expanded our understanding of the cosmos. There will be more discoveries to come, more mysteries to solve, and more wonders to behold. The universe is vast and ancient, and we have only just begun to scratch the surface of its complexity. Every new observation brings us closer to understanding the full story of how the universe came to be, how it evolved, and how it will continue to change in the future. And that story is one of the most profound and awe-inspiring stories ever told. The discovery of 300 impossibly bright galaxies in the early universe is a milestone in our quest to understand the cosmos. It is a reminder that the universe is full of surprises, that our models are always works in progress, and that the pursuit of knowledge is an endless and endlessly rewarding journey. These galaxies are not just distant points of light. They are windows into the past, allowing us to witness the birth of the universe and the formation of the first structures. They are teachers, showing us what we got right and what we need to rethink. And they are inspirations, reminding us of the incredible beauty and complexity of the universe we inhabit. As we continue to study these galaxies and as we await the next wave of discoveries from James Webb and other telescopes, we can take comfort in the fact that the universe is not done surprising us. There are more mysteries out there, waiting to be uncovered. There are more impossible galaxies, more enigmatic objects, and more profound questions about the nature of reality. And there are more opportunities for us to learn, to grow, and to deepen our understanding of the cosmos. The 300 galaxies are just the beginning of a new chapter in the story of the universe, and it is a chapter that promises to be every bit as exciting and enlightening as those that came before. In the grand scheme of things, the discovery of these 300 galaxies is a testament to the power of human curiosity and ingenuity. It is a reminder that despite our small size and short lifespans, we are capable of understanding the most fundamental and far-reaching aspects of the cosmos. We can peer back in time to witness the birth of galaxies. We can measure the expansion of the universe. We can test our theories against the evidence and revise them when necessary. This is the essence of science, and it is what makes the study of the universe so profoundly meaningful. So, as we reflect on the discovery of these 300 impossibly bright galaxies, let us celebrate the progress we have made and look forward to the discoveries yet to come. Let us embrace the mystery and the uncertainty, knowing that they are the fuel that drives scientific inquiry. Let us appreciate the incredible tools and technologies that make these discoveries possible, and let us support the continued exploration of the cosmos. And let us never forget that the universe is a place of wonder, a place where the impossible can become possible, and where the quest for knowledge is a journey without end. The James Webb Space Telescope has given us a gift, a glimpse into the early universe that is both thrilling and perplexing. The 300 galaxies it has discovered are challenging our understanding of cosmology, pushing the boundaries of what we thought was possible, and inspiring a new generation of astronomers to think boldly and creatively about the nature of the universe. As we continue to unravel the mystery of these galaxies, we will learn more about the birth of the cosmos, the formation of the first stars and galaxies, and the fundamental laws that govern the universe. And in the process, we will gain a deeper appreciation for the incredible beauty and complexity of the cosmos and for our place within it. This is a time of great excitement in astronomy. We are living through a golden age of discovery, with new telescopes and new technologies revealing the secrets of the universe at an unprecedented pace. The 300 impossibly bright galaxies are just one example of the many wonders that await us as we continue to explore the cosmos. There will be more discoveries, more mysteries, and more opportunities to learn. And as we journey deeper into the universe and further back in time, we will continue to be amazed by the richness and diversity of the cosmos. The universe is full of surprises, and it is up to us to uncover them. The story of these 300 galaxies is far from over. It is a story that is still being written, with each new observation adding a new chapter. As astronomers continue to study these galaxies and as they gather more data, the picture will become clearer. We will learn whether these galaxies are powered by stars or black holes, whether they are as massive as they appear, and whether they require us to revise our models of cosmology. We will learn about the conditions in the early universe and the processes that allowed these galaxies to form so quickly, and we will learn about the limits of our knowledge and the frontiers of our understanding. In the end, the discovery of these 300 galaxies is a reminder that the universe is a place of infinite wonder and infinite mystery. It is a place where the rules can be bent, where the impossible can happen, and where the pursuit of knowledge is a never-ending adventure. It is a place that challenges us, inspires us, and humbles us. And it is a place that we are privileged to explore, one discovery at a time. The 300 impossibly bright galaxies are a testament to the power of the universe to surprise us, to the power of human curiosity to uncover its secrets, and to the power of science to transform our understanding of reality. As we look to the future, we can be confident that the universe will continue to reveal its wonders to us. The James Webb Space Telescope is just the beginning. There are other telescopes on the horizon, other missions planned, and other technologies being developed that will allow us to see even deeper into the cosmos. Each of these tools will bring new discoveries, new insights, and new mysteries. And each of these discoveries will bring us one step closer to understanding the full story of the universe, from its birth in the Big Bang to its ultimate fate billions of years in the future. The 300 impossibly bright galaxies are a signpost on this journey, a marker of how far we have come and how much further we have to go. They are a challenge to our current understanding, a mystery to be solved, and an inspiration to keep exploring. They remind us that the universe is not a simple place, that it does not always conform to our expectations, and that there is always more to learn. And they remind us that the pursuit of knowledge is one of the most noble and rewarding endeavors that humanity can undertake. It is a pursuit that connects us to the cosmos, that reveals the beauty and complexity of the universe, and that gives us a sense of our place in the grand scheme of things. So, as we close this chapter and look ahead to the next, Let us remember the 300 galaxies and the questions they have raised. Let us continue to support the exploration of the cosmos, to invest in the tools and technologies that make these discoveries possible, and to celebrate the achievements of the astronomers and scientists who dedicate their lives to understanding the universe. Let us embrace the mystery and the wonder of the cosmos, and let us never stop asking questions, never stop exploring, and never stop reaching for the stars. The universe is waiting, and it has so much more to show us. And that wraps up our incredible journey into the mystery of the 300 impossibly bright galaxies discovered by the James Webb Space Telescope. What an incredible puzzle they present, right? From challenging the very foundations of cosmology to forcing us to reconsider how galaxies form and grow, these ancient light sources are reshaping our understanding of the early universe. If you found this cosmic exploration as fascinating as we did, we would love for you to join us on this ongoing journey of cosmic discovery. Hit that subscribe button and let us know in the comments what you think about these impossible galaxies. Are we witnessing a revolution in cosmology, or is there a simpler explanation we have not yet considered? Thanks for watching, and until next time, keep looking up.